Hello everyone. Now I will explain how to do the fault calculations in this problem. So for this, what I need to do. So first of all, to calculate the LG fault current. Okay. So in the problem, it is given fault is occurred on the third bus. So if you want to calculate the fault current, so what is fault current formula? IF is equal to 3ER1 by x1 plus this is x1 equivalent and x2 equivalent plus x0 equivalent, zero sequence equivalent. So from this what we need to calculate, so ER1 is the positive sequence voltage, this is in per unit. If not mentioned anything, you can take 1.0. Here fault voltage is not mentioned, so you can take 1.0. Now you want to calculate x1 equivalent, that is positive sequence network of given power system network. Similarly, you need to calculate negative sequence impedance and you need to calculate zero sequence impedance. Okay, for that, what I need to do, first I need to draw the positive sequence impedance. Okay, these are the given values. Here, in the table, if you observe this one, this is positive sequence values of the, this is the generator 1, generator 2, transformer 1, transformer 2, and this is transmission line impedances or reactances. Similarly, these are the negative sequence and these are the zero sequence reactances. Okay, now first I'm doing, so this is the given diagram. So what I'm doing, simply I'm rotating this diagram. Okay, if I rotate this diagram, the diagram will becomes like this. So here now the fault is occurred. First what we need to do, first we need to draw the positive sequence diagram of each component, that is for generator, transformer, transmission line, as well as this transformer, this generator. So if you draw the first positive sequence network of first generator, so what we need to do, the positive sequence network for generator is like this. Okay, this is internal induced EMF ER1 and the internal reactance X G1. Okay, the reference for the positive sequence is neutral, it is represented with the dotted line. So, and if you draw the positive sequence network or diagram of the transformer, simply this is the positive sequence diagram. Similarly, for the transmission line, same as the transformer. So if you draw the combined network for the total network, that is total power system, so you can draw the generator 1, this is ER1 and this is X1 of first generator and next one. So for generator 1, positive sequence diagram is completed. And then E1. Next we have a transformer. So positive sequence diagram of transformer is simply reactance. Now coming to this side, okay, both generator and transformer are completed. Now coming to this side, same we will get, this is for generator for positive sequence network and this is the transformer positive sequence network. Now we need to draw the line diagrams. So line diagrams also same. These are the connections. Here the fault is occurred, that means we need to calculate x1 equivalent here. Okay, so this is the neutral point and here also we have a neutral point because it is a positive sequence. So it is neutral point means all these are connected. All these are connected. This is the dotted line. Okay, so we need to calculate here. So whenever you want to calculate the reactance, resistance or impedance, so what we need to do, we need to replace the voltage sources with short circuit and the current sources with open circuit. Then we will get the network becomes like this. Okay, so this is the internal reactance of the synchronous generator, and it is given as how much it is given. This is 0.15 positive sequence as well as negative sequence 0.15. So this is the 0.15. And the for transformer it is given as the 1.1. Okay, here this is 0.1. Similarly, it is 0.15 and this is 0.1. Okay, the line it is given as 0.125, and here the line it is given as 0.25, and here the line it is given as 0. Now these two reactances are in series. Let us take reactance A, and these two reactances are in series. Let us take the reactance is B. Now convert this delta. Okay, this is delta. Convert this delta into star network. Then you can get like this. Okay, now finally if you draw the network, if we redraw the network, this is equivalent reactance, let it be A, and here the equivalent reactance, let it be B, and this is the connection. Here we have a star equivalent. Let us consider this is C, D, E. Okay, now this is E, this is C, this is E, and this is D. So here we need to consider positive sequence. Okay, now A and C are in series and B and D are in series. Then the network becomes like this. Here we need to find the x1 equal. Okay, for positive sequence equal. In previous what we take A, B, C, D. D is here. Let's take it is equivalent F and it is G. Now F and G are in parallel because these 2 points are connected here and these 2 points are connected here. So this is parallel equivalent. Let us take H and this is D. Here we need to calculate x1 equivalent. Now finally H and D are in series. Then finally we will get a single equivalent network. So this is the x1 equivalent. Okay, totally finally you will get one value, that is the x1 equivalent. Now if you want to draw the negative sequence diagram, what we need to do, one negative sequence network for generator, the negative sequence network, again it is a neutral point. The internal induced EMF is 0 in case of negative sequence, only we have a reactance, that is internal reactance. This is the VR2. VR2 is the 0 and this is the X2. Okay, so similarly for transformer, this is the diagram. Similarly if you draw the transmission, this is the diagram. If you draw the combined diagram, then for positive sequence diagram of this generator 2 is only we have reactance for transformer, again we have reactance. Similarly, bottom generator, and this is the bottom transformer, and here we have a transmission line from 1 to 2. Okay, this point to this point, this point to this point we have this reactance, that is 0.125, and here we have a delta connection, and it's 2 equivalent here. Okay, this is the negative sequence diagram, and actually this is the neutral point. Okay, for typing I'm writing here a solid line, but it is a dotted line, so we need to calculate x2 equivalent. Okay, same story, that is this is 0.25 and this is j 0. Can take j or not. Okay, no problem, that will decide the magnitude and phase angle. So again these two are in series, and these two are in series, and again here convert the star connection. Okay, then again these two are in series, these two are in series, again these two are in parallel, and the final value is series to this one. Okay, same as positive sequence, no problem. So almost you will get x1 equivalent is equal to x2 equivalent. Okay, now we want to draw the zero sequence network. This is our given power system network. Now the zero sequence diagram of a generator is internal impedance is 0, and this is the neutral reactance, and this is the internal impedance. This is 3. That means here the reference is ground, that is solid line. So here it is AR1, and here it is X0. This is the X0. When this is 3x. For suppose if fault impedance is given, so what we need to do, if fault impedance is given, we need to add zero sequence, that is 3z. Okay, so first we need to calculate without fault impedance. So this is the zero sequence diagram of the generator. So zero sequence diagram is 3xn, that is 3 into 0.25 by 3. It is given in the problem. Then we will get 3 gets cancelled, and this is the zero sequence of synchronous generator. So how much it is given? It is given here 0.05 for generator, 0.1 is for transformer, and 0.335 and 7.25 is for transmission lines. Now if not mention anything in connections, that is a transformer connection, consider this is delta and this is star with solid grounding. Okay, star with solid grounding. So for transformer, what is the zero sequence diagram? Already I have given in the clarity in class. So this is, we have a series switches, and these are the parallel switches. If the delta connection is given, we need to close parallel switch. If star connection is given, we need to close series switch, but consider neutral reactance also. Okay, so here neutral reactance is solid grounding, so consider yeah, that is secondary side. So we need to close this switch and we need to close this switch. Why? Because it is a delta star connection and with solid grounding. So solid grounding is given, so that internal impedance is short circuit. So this is the diagram. So if you draw the diagram for transformer, and this is parallel switch, and this is the reactance of transformer, and the internal that is neutral grounding is 0, so short circuit. Now coming to transmission line, this is the zero sequence diagram of the transmission line. So here the fault is occurred here, we need to calculate X not equivalent here. Similarly, if you draw the zero sequence diagram for 102, this is neutral reactance, this is internal reactance, and this is the transformer. Now we need to close parallel switch, and this is for transformer. Neutral is 0, that is solid grounding, so equal to 0. So this is the diagram. Now this is ground point as well as this is the ground point as well as this ground point. That means all these 3 points are same potential, so you can add the open circuit, so you can calculate this one. Okay, here also we have 3 into 3xn, so xn is given 0.25 by 3. Here 3 gets cancelled, but the generator is isolated because of the delta connection, so only you need to consider the reactance of transformer, zero sequence reactance of the transformer. So this is 0. Per lines it is given 0.3, 0.35 and 0.7125. So this is 0.3 and 0.35. What we need to do again, you can convert same story, this delta into star, and this is star function. So finally this is star, this is star connection, again transformer, star connection impedance, this is star connection impedance. So suppose let us take this is A, B, C. So this is A, B, C. This is 0.1, this is 0.1. So you can calculate X naught here. Okay, so these two are in series and these two are in series, and resultant is in parallel. Again this one and this one in series. Finally you will get the X naught equivalent. Now what is the fault current in case of LG fault? So if LG fault, so IF is equal to 3 ER1 by X1 equivalent plus X2 equivalent plus X0 equal. Now in case of this is for LG fault, for LL fault this is root 3 ER1 by X1 plus X2, this is equal. Okay, why? Because here LL fault there is no grounding effect. If there is no grounding effect, there is no zero sequence. Now coming to LLG, so coming to LLG, it is somewhat difficult. For LLG fault, the fault current is 3 IR. Whatever the IR naught is equal to X2 equivalent by X2 equivalent plus X0 equivalent into IR. Now what is IR1? IR1 is equal to, I will write here, IR1 is equal to ER1 by X1 plus X2 equivalent in parallel with X0 impedance. For suppose if fault impedance is given, we need to include fault impedance here. This is in case of, we need to substitute here. This is in case of LLG fault. Okay, this is for LLG fault. Now for triple L fault, it is very simple. IF is equal to AR1 by X1 equal. Okay. If fault impedance is given, simply we can have accept fault. Okay. Now if fault impedance given, what we need? So if you observe this one, this is for LG fault. This is for LG fault. So here the fault impedance is included here. Only 3ZF. Only 3ZF. So if fault impedance is given for LG fault, if grounding effect is there, you need to multiply with 3. Otherwise, no need to multiply with 3. So this is 3ZF. Now coming to LL fault. This is LL fault. So this is LL fault. So here we're adding ZF, only ZF. Okay, we are not adding 3ZF. Why? Because it is in this part we don't have any grounding effect. So simply we have ZF. Now coming to LLG fault. Here there is a grounding effect. Here there is a grounding effect. So we need to add this in zero sequence diagram. Zero sequence diagram, there is the 3ZF. Okay, so if you calculate the zero sequence diagram for LLG fault, so what is the Z0 equivalent? Z0 equivalent is equal to 3Zn plus Zg0 plus 3Z. Okay, so you need to add these three things. Z0 equal. Now coming to triple L fault. Triple L fault already we have discussed. So IF is equal to AR1, yeah, simply X1 plus XF or ZF. Okay, we can take, and here only reactance is mentioned, so we can take XF. So by adding 3ZF, we can get the answer. That means for LG fault, IF is equal to 3ER1 by X1 plus X1 equivalent plus X2 equivalent plus X0 plus 3ZF. X0 equivalent plus 3ZF. We are calculating the X0 equivalent. Similarly, IF for LL fault, that is 2 3ER1 by X1 equivalent plus X2 equivalent plus ZF only. Okay, this is LL fault. Now if you want to calculate fault current for what this one for LLG fault, this is 3IR0 3IR0. Okay, this is 3IR0. So what is IR0? IR0 is equal to opposite impedance Z2 equivalent by Z0 equivalent plus Z2 equivalent into IR1. Here there is Z0 equivalent, so we need to add 3ZF here. Why? Because this one is 3ZF. That 3ZF is added in the zero sequence network. So you need to add 3ZF in the zero sequence network. That means if you want to calculate IA0, this is our total current IA1. This is IA2. So if you want to calculate IA0 here, so IA0 is equal to opposite impedance. Opposite impedance is Z2 by total impedance. Actually, we calculate up to here, that is Z0 equivalent. Now you need to add 3ZF for the fault impedance is given. So this is Z2 plus total impedance is Z2 plus Z0 equivalent plus 3ZF. This is IA0. Actually here it is minus, and this is the IA. Now what is IA1? IA1 is equal to ER1 by X1 plus X2 parallel with X0 equivalent. Right? Actually this is also equivalent, this is also equivalent. So here we have a again zero sequence network. ER1 by X1 equivalent plus X2 equivalent plus here parallel. This is parallel. Parallel means X0 equivalent plus 3Z. I need to add here. That means X2 equivalent and X0 equivalent plus 3Z are in parallel. This is a combination for in parallel. So from this we can calculate the fault current. Okay. So this is about the fault calculation of the sixth problem. I think it is fifth problem.